Right. So now we have let's say, more overview to the physics of the muon collider from Xing. I'll give you the time.
Okay, thanks for having me to give this talk here. So now we have heard a lot about going outside the box. Now let's come inside the box and see what we have there. Just a very brief introduction. So the standard model has been really kind of successful for us. Ever since the electron was discovered, say, 100 years ago, until the most recent 2012, the discovery of the Higgs, we have already completed all the particle content of our standard model. So this has been a huge success for our field. But of course, we know that the story doesn't stop here. For the standard model, we still have a lot of issues and questions that we want to some extent get some answers about. For example, here is just an incomplete list of all the questions that we care. For example, the hierarchy problem, why there's a huge gap between, say, our electroweak scale and the, say, for example, Planck scale. And also, so far, we have no evidence in our laboratory about what's the nature of the dark matter. And of course, we have observed the neutrino oscillation, which is not explained within the standard model. And also, there are matter asymmetry that we need to address to explain our existence, basically. So in this talk, I will be talking about the muon collider, of course. So the question we ask is, what can we learn at the muon collider? Right, so just a very, very brief introduction, or kind of just to remind you what muon collider is. So muon collider we're talking about is basically a 10 TeV muon collider. It's a special opportunity that offers us to build a rather compact machine. You only need, roughly speaking, the size of the LHC to achieve a 10 TeV collision. And also because muon is 200 times heavier than electron, you suffer much less radiations. And of course, muon in comparison to protons is really kind of like a point-like particle. So in that sense, once you collide, once you have head-on collision of mu plus mu minus, you really can have the chance to maximally make use of all the collision energy here. And of course, building muon collider is not easy. It's actually quite challenging work. So not only from the accelerator side, but also the detector side. And I won't really talk any more than this, but I refer to some of the previous talk where you can take a look at all the kind of major challenge that we're facing right now. But however, I want to emphasize that here because very often challenging is also synonymous to exciting. So the muon collider is also kind of give us a very exciting opportunity, not only physical in terms of probing new physics, but also technological side. It's also very interesting, a exciting project to work on. Okay, so now let's get into the main topic of this talk. So in this talk, I will basically talk about some of the important physics cases that you can do at the muon collider. So first, I will be talking about some of the standard model physics you can do at the muon collider, and then I will go into the beyond standard model physics, and in particular, I will focus on the BSM physics at the energy frontier and as well as the precision frontier. And in the end, I will conclude. Okay, so now let's talk about the standard model physics first. And of course, if we build the muon collider or any collider, the first thing we want to do is to measure the Higgs, right? Because Higgs is currently really serving as a lamppost for us to look at, to try to look beyond the what could happen beyond the standard model. So one thing we will do for sure, whether it's FCCE or Muon collider, is that we will have very precise measurement of the Higgs coupling. And in particular, at the Muon collider, at this multi-TeV regime, you will actually produce tons of Higgs through the so-called VBF processes. And roughly speaking, you will produce order of millions or beyond Higgs at the 10 TeV Muon collider. So you can immediately just translate this number of Higgs into the precision we should expect. So we should therefore for the coupling we should really expect something of order 10 to minus 3 precision at the Muon collider. Right. For example, in this plot, it shows you the achievement on all the Higgs coupling measurement you can achieve in terms of the kappa scheme. And as you can see, for many kind of couplings, you can definitely go beyond the 1% level at the 10 TeV Muon collider. And of course, all the measurements about Higgs, the most important thing we are interested in is the Higgs self-coupling. Because the Higgs self-coupling so far is the least measured standard model parameter. And it's very closely linked or related to the origin of the electroweak symmetry breaking. So therefore, precise measurement of this self-coupling may tell us what's going on with this electroweak symmetry breaking. And of course, we have already learned that the Higgs self-coupling in particular, it's not that easy to measure at the LHC because of the destructive interference. And actually, so this nice plot sketch show you the kind of improvement we can get on the knowledge of the Higgs potential from what we have right now at the LHC to high lumen LHC. So of course, I think it's already very impressive that at the end of the high lumen LHC, we will be able to observe this di-Higgs channel, and which also constrain the Higgs self-coupling to the precision of about 50 to 60%. And of course, on the other hand, at the FCCE or CEPC, because the energy budget there, you cannot really produce the Higgs pair there. So at those low energy kind of 100 GeV-ish machine, you can only measure the Higgs self-coupling through some of the loop effects. But of course, if we go to a 10 TeV Muon collider, we'll make plenty of Higgs pairs. So here, this is just some benchmark cross sections for different collision energy with corresponding luminosity at the Muon collider. So basically, at the future Muon collider, we will be able to produce Higgs pairs of order, 10 to 3 to 5th power Higgs pairs. So which tells us, again, you just take the 1 over square root of n estimation, we can get the precision on the measurement of a percent or per mil level on the couplings. So, so therefore, the Muon collider really offers us an opportunity to precisely measure the Higgs self-coupling. For example, there has been a lot of work studying this self-coupling measurement. So the bottom line here is that at the 10 TeV Muon collider, we will be able to basically achieve the precision of 5%-ish. So here, this is kind of a comparison on the precision on the Higgs self-coupling among different colliders. And as you can see, the Muon collider at 10 TeV really kind of it's really kind of advantages in terms of understanding the Higgs self-coupling here. And so therefore, by measuring this self-coupling at the muon collider, we will be able to actually tell what the Higgs potential look like, whether or whether it's really predicted as the standard model. And of course, other besides all the kind of a standard measurement we can do at the future collider, here I want to argue that at 10 TeV muon collider, you really start to see some kind of new, well, still standard model, but some new phenomena start to emerging at such multi-TeV scale. For example, if you go to energy much larger than the electroweak boson masses, then you will start to see the electroweak symmetry group approximately unbroken. So therefore, you will start to see the restoration of the electroweak groove. Therefore, at such high energy, the electroweak radiation will start to behave like a QCD does. For example, in the QCD, we are all familiar with the story where you can use a certain kind of parton model to describe the collision of proton, and also there are a lot of kind of QCD showering going on. So those would be very interesting phenomena to observe for the electroweak interaction. So therefore, if you go to very high energy, so even the muon start to have very kind of rich parton contents due to this electroweak radiation. Right. For example, here in this sketch, I'm just trying to show you all different kinds of possibility you can actually get out of the muon. And I think among all of them, I think the most interesting one is that you can even start to get gluon out of muon through all those kind of radiation here. And of course, at high energy, we know that the electroweak radiation will be enhanced by this logarithm log of Q over mW here. So therefore, this kind of high energy behavior really kind of encourage us in some sense to describe such behavior using the kind of parton distribution function type of manner. So for example, this plot shows you the kind of the parton distribution function of different content from muon as a function of the energy fraction. So of course, here you can see you not only get a lot of photon or W and Z boson, you also get quite a significant amount of gluon or even quarks, especially at low X, low energy fraction here. And of course, also worth mentioning is that again, you also get a lot of neutrinos out of here. And of course, so far this is a really kind of a rather kind of empirical description we have been kind of using. So, and this idea is not new, right? So this the first discussion about all these effective W approximation was something like 40 years ago. And at that time, people already tried to write down the scattering of vector boson using this kind of factorization ish kind of a form. But of course, we know that the electroweak radiation may behave like QCD radiation, but we know there is a very kind of distinct difference between those because after all, the electroweak group is broken, right? So which means the electroweak symmetry is only restored at a very high energy, the energy much larger than the vacuum expectation V here. And of course, when we say restoration, we doesn't really mean V equals 0. So V is so the VAV will always be there. It's just that if you go to the energy scale much larger than V. So therefore, this finite V means that the electroweak theory will have a physical IR cutoff of order MW. And another important feature of this is that in QCD, we don't observe color, right? We only observe a color neutral subject. So therefore, whenever we do measurement, we measure something inclusive. However, for the electroweak group, the electro color or here, whether it's a neutrino or it's a muon or it's an electron, that's something observable. So therefore, for the electroweak group, we don't have this kind of generically this kind of inclusive measurement. So this would lead to a problem like incomplete cancellation of logs. So basically, I won't go into detail, but let me just say that I think this is still a very active field, and there are many questions to be addressed because we know that this factorization is cannot be exact. So there are a lot of work that need to be done and will be done along this direction. And of course, another thing we can do, of course, I'm still talking about the standard model measurement here, is that the muon collider really offers us a very high energy and high quality neutrino beams, as we have already heard from previous talk by Jen here. So basically, by making use of the muon decay, we actually can produce a very high energy neutrino flux, and which is very perturbatively calculable here. So here I'm just trying to give you one example that how we can make use of this neutrino beam is that you can do things like a neutrino deep inelastic scattering here. So for example, this would be if you have a neutrino goes in, interacted with your target through some charge current, and then you can use this to probe, for example, the parton distribution function here. Here in this plot, this shows you the 2D distribution of the x-axis is the energy fraction, and the vertical axis is the momentum transfer q square. And as you can basically see, the majority of the neutrino scattering happens at the order of q square equals to 1,000. And also a relatively large x here. So which means in this region, our perturbative calculation is very reliable to compute everything here. And on the right-hand side, this shows you some study on the improvement of the PDF uncertainty. And as you can see, in comparison to what we currently have at the LHC, by doing this neutrino DIS, you can really improve the PDF uncertainty by quite a bit. And also, people have studied, also at the same time, you can also use this the DIS to also study and constrain the CKM matrix in the quark sector here. And again, as you can see, you will get a large improvement in comparison to the current measurement we have. Okay, so now I want to go to the beyond standard model searches that we can do at the Muon collider. So of course, one thing I want to talk about is the so-called minimal dark matter model. So minimal dark matter model is a very simple model. It's well motivated, but however, it's really hard to discover those models so far. So just to put in short, this model is that you assume the dark matter is charged under the standard model SU2. So according to the representation, you can classify them into either doublet, triplet, and so on and so forth. And among those, the most kind of famous models are whether either you have a Wino-like model or you have a Higgsino-like model. And here, in this plot, this is the current constraint from direct detection by LZ experiment. And as you can see, for the pure Wino model and Higgsino model, it's still beyond our current reach from direct detection. And in particular, the Higgsino model, the cross section is way below the neutrino floor. So therefore, they are very, very hard to discover, even though the model itself is really, really simple. And of course, and also currently, we also have bounds from the, for example, searches at the RHC, but unfortunately, the current bound is only of order of a few 100 GeV. But however, to be able to which is way below the thermal target that we want to shoot for. So the thermal target is the mass that where these dark matter models saturate the observed relic abundance. And as you can see, for the Higgsino, the thermal target is really 1 TeV, and for the Wino, it's 3 TeV. So they are really ideal target to search for at the Muon collider. So here, and of course, at the Muon collider, we can look for those Wino and Higgsino dark matter through different channels. For example, we can use the so-called conventional missing mass searches, where you can look for monomuon searches, where the signature is that you observe a apparent charge imbalance at your detector, and again some momentum imbalance here. And also you can search for mono X searches. This X can be photon, can be W. And also you can search for dimuon searches. And so the constraint is shown in this plot, where the green color stands for 3 TeV Muon collider, and the red color stands for the 10 TeV collider. And the dashed line here represents the thermal mass, 1 TeV for the Higgsino and 3 TeV for the Wino dark matter here. And of course, you can also search for this kind of dark matter model through exotic signature, which is induced by the compressed spectrum of this model. So for the pure Wino and Higgsino dark matter, the typical mass splitting between the charged state and the neutral state is only of order 100 MeV. So therefore, the charged particle will become long-lived, and the typical lifetime is of order 0.01 to 0.1 nanosecond. So therefore, if you produce this particle at the collider, so they will give you some very distinct signature here. For example, you can have disappearing track searches, where you, from your primary vertex, you first produce the charge state, and after traveling a kind of a microscopic distance, typically of order 5 to 12 centimeter, and then it decay to a very soft pion, and then some neutral component, which it's invisible at the detector. And on the other hand, you can also, instead of searching this red line here, you can actually also look for this curved green line, which is the soft pion signature. And the sensitivity you can get from this exotic signature are also shown in this plot, which are the monophoton plus 1 or 2 disappearing track signature, or you can look for the soft tracks signature here. So basically, I think the bottom line here is that by making use of all these conventional and exotic signature at the 10 TeV Muon collider, we can give a very definite answer to whether the Higgsino or Wino dark matter it's realized or not. And of course, you can also look for other kind of beyond standard model signature as well. So here I'm just trying to go through some of the very kind of representative and also very simple model. For example, you can extend your standard model by adding a singlet scalar here. So basically, what you so therefore you will basically have a heavier scalar or heavier Higgs, and it will naturally mix with our standard model Higgs here through this, which can be characterized by this mixing angle gamma here. And of course, at the Muon collider, you can either search this indirectly by precisely measure the Higgs coupling, because all the standard model Higgs coupling now, because due to this mixing, will be modified by this mixing angle. So therefore, if you we can either kind of, so basically we can probe such new physics by precisely measuring the Higgs coupling. And in this plot, this shows you the sensitivity at the Muon collider. So x-axis is the mass of this heavy scalar, and the y-axis is the mixing angle sine squared gamma here. So as you can see, this dashed horizontal line, they come from this indirect probe where you simply measure the standard model Higgs coupling. But on the other hand, because now we have 10 TeV energy budget, why not why don't we just produce those heavy states directly? So those are typically done by the vector boson fusion processes, which the corresponding sensitivity are shown here by these solid line here. And as you can see, especially in the region between these two dashed lines, which are more kind of motivated from a theoretical point of view, that as you can see, the Muon collider is really kind of advantageous, not only in comparison to the LHC, but it's also exceeds the sensitivity of the FCC-HH by a large amount in those regions. And of course, since we, for the direct detection, as we really kind of try to directly probe this kind of heavy state, we can really go to the allowed kinematic region, which is 10 TeV here. And of course, there are other kind of simplified model. I think the most representative one is the 2 Higgs doublet model. And you can also search for the 2 Higgs doublet model. And in particular, if you stick to the kind of the alignment region, then the signature at the future Muon collider will be the pair production of the heavy Higgs either charged or the CP odd or CP even heavy Higgs. They will be produced through Z or gamma intermediate state in pair here. And so here this plot shows you the reach you can get at the Muon collider for different type of 2 Higgs doublet model. And depends on which kind of decay channel you look for. But I think the bottom line here is that the reach you can get at the Muon collider is really kind of maximally a square root of S over 2 because you produce those heavy states in pair. And of course, we can also search for a heavy neutral lepton. So this heavy neutral lepton is really kind of ubiquitous in different beyond standard model. So where you want to address the neutrino mass problem here. And in particular, if the heavy neutral lepton have a significant mixing with the second generation here, you can actually produce through this T-channel diagram, which give you a very large rate in comparison to other S-channel or VBF processes. And in this work, the sensitivity you can achieve at the Muon collider is estimated by those dashed line in red and orange here for 3 and 10 TeV Muon collider. And as again, you can really see that since here we are kind of singly produce this heavy state, we can really go to all the way approximately up to the kinematic threshold, which is 10 TeV at the Muon collider here. And again, here is just a comparison where the lower two lines are for the neutrino that prefer the second the second generation. But if you if they only sensibly coupled to the first or the third generation, then of course you get much weaker bond due to because in those cases you don't have the T-channel enhancement as this plot here. Okay, so that's all the kind of representative BS model or I want to talk about, which really kind of the kind of the take-home message here is that at the 10 TeV muon collider, you can really just start to probe those heavy states up to 10 TeV or 5 TeV if they can only produce in pair. But now I want to also talk about the BSM precision from energy. So I think the important message here is that at the 10 TeV muon collider, we not only can probe heavy physics up to 10 TeV, we can actually even go way beyond the 10 TeV scale. For example, in this plot, they show the sensitivity at the muon collider for some models like Z prime or some composite Higgs models. As you can see, the constraint you can set at 10 TeV muon collider can go up to order of 100 TeV each. Depends on the size of the strength of the coupling here. The observable here, I think it will be just a dilepton. I have to check. I think the signature here would either be dilepton or dijet signatures. So here, let's try to characterize this kind of precision from energy behavior. So we are all very familiar with the standard model EFT, which has been shown to be very useful to characterize all the indirect effects from BSM physics. For example, you can have this power counting in terms of lambda, and in particular, for example, here, if you consider a dimension 6 operator, then the contribution to the scattering amplitude will typically goes as these three terms. They can either, just by dimensional analysis, they either goes as v square over lambda square, or they can go as e square over lambda square. So now, if you go to measure such effect at high energy muon collider at energy scale e square much larger than the v square, then the BSM contribution will be naturally have this e square over lambda square behavior here through the interaction, through the interference between this dimension 6 operator and the standard model contribution here. So therefore, you can immediately make use of this e square over lambda square behavior to have a rough estimation of what kind of precision we can achieve. Let's just take the simplest 1 over square root of n naive estimation. So then you can immediately translate this into the cutoff scale here. So basically at the collision energy of 10 TeV, if the BSM contribution is of order 1 femtobar with 10 inverse, I forgot to change the units here. With 10 inverse attobar luminosity, then you basically can achieve the, you can probe the cutoff scale up to 100 TeV here. And so now let's go to some more specific processes you can consider, right? So the simplest thing you can consider is just the 2-to-2 processes here. And in particular here, if you consider the certain 4 fermion interaction at the dimension 6, you can immediately compute the amplitude, and indeed gives you this e square of lambda square behavior. And you can also consider other kind of 2-to-2 processes, which are probe different set of dimension 6 operator. But again, the bottom line is that they all give you a behavior go as e square over lambda square here. So therefore, if we collide those muons at the 10 TeV energy, then even as long as we can measure the cross-section up to 1% accuracy, then we can translate this precision into the the BSM scale lambda of order 100 TeV, as long as this new physics is coupled to muons. And so here is just some of the math feat you can do with all different kinds of operator, whether it's a mu mu HH operator or the mu mu LL for fermion operator. And then as you can see, so at the muon collider, you can basically go above 100 TeV cutoff scale here. And of course, you can also look instead of you can also look for the digest final state. And again, for all those for fermion operator, as long as the muons are involved, you can again probe the new physics up to 100 TeV scale here. And of course, if you can also do flavor physics here. So if you look for some flavor changing final state, then you can again probe the new physics up to of order 50 to 100 TeV scale. And in many cases, you get much better sensitivity in comparison to the low energy experiment, particularly due to this E square of lambda square effect. And of course, beyond the 2-to-2 processes, we can also study the those BSM effect using VBF processes. But of course, I have to admit, I have to confess here that the VBF in general has much weaker sensitivity compared to the direct annihilation processes. For example, in this plot, this is a really kind of a zeroth order estimation of what kind of energy you can probe through the VBF processes. Here you can use the effective double approximation and approximate your signal by assuming it's dominated by the fusion of longitudinal boson. And then for the background, it could be either transverse or longitudinal boson fusion. And then for the standard model, I just assume it's 1. Okay, it's the number itself doesn't matter, but standard model, I assume it's basically grows as a constant over energy. And then for the BSM cross section, it goes as this S over lambda square. Right. So then using this very simple formula, you can immediately estimate the S square the sensitivity S over square root of B. And as you can see, if the most sensitive result come from the S hat, the energy scale of your Hart scattering of order 3 to 4 TeV. Right, so because you're doing VBF, you cannot make use of the full 10 TeV energy, but nevertheless, you can still go as high. You can go to a few TeV, and here 3 to 4 TeV gives you the most sensitive bins here. And another thing is that we can use VBF to probe operators that are not directly accessible through annihilation processes. For example, they are not directly coupled to muons. Then we can probe them using VBF processes. For example, we can study the Higgs production through VBF, or the difermion production, where the fermion can be either quarks or in other words jets, or they could be either electron or taus. Here I skipped muons because for muon final state you can actually probe them better through just mu mu to VV 2-to-2 processes here. And also you can have vector boson scattering, which they all can be kind of have this E square over lambda square behavior induced by all different kinds of dimension 6 operators. And in this plot, just show you the sensitivity you can get from the Higgs channel here. So in particular, these 6 operators will affect the Higgs production at the muon collider. And in particular, the first C5 and C5 box, they are related to the modification of the Higgs self-coupling here. And as you can see here, at the Muon Collider, you can really improve a lot in terms of the new physics scale here. Okay, now let me summarize. So in this talk, I tried to argue that Muon Collider not only kind of probe exciting new physics, but it's also a very kind of challenging technologically. So therefore, it's also a very exciting project to work on, because after all, we have never have muon as our as the particle to collide. And of course, I argue that at the Muon Collider, we not only measure standard model precisely. That's all. That thing you can do either at Muon Collider or you at FCCEE. But I want to emphasize that at the Muon Collider, at this multi-TeV or 10 TeV energy region, you will start to also see new standard model phenomena, such as the electroweak radiations here. And of course, through a direct kind of probe, you can kind of probe beyond standard model state up to either square root of s over 2 if they are pair produced, or square root of s if they can be singly produced. And again, the Muon Collider is also a precision machine that it's especially amplified by this energy growth behavior induced by some heavy BSM effect. Then we can use Muon Collider to probe such effect up to 10 to order of 10 to 100 TeV. Thank you.
Thank you, Xing, for this very good summary. We have comments or questions.
Hi, thanks, Xing, for the wonderful summary. Could you please go to slide 13? Yeah, the one.
Here?
Yeah, so here in this second
Sorry.
the Muon Collider at 3 TeV, is it giving a better precision than 10 TeV?
No, so sorry, this orange box is the 3 TeV,
Yeah,
and this box is 10 TeV.
So why is the orange bar higher than 10 TeV? What does this say?
Sorry, the y-axis is your precision on this self-coupling, right? So at 3 TeV, the kind of uncertainty is much higher. So sorry, your question is why?
Yeah, why is 3 TeV giving a better precision than 10
No, it's worse. It's worse. Yeah, the lower the better.
Oh, the uncertainty is more in 3 TeV.
Yeah.
Okay, thank you.
You had no time to touch upon it a lot, but do you think you can use to characterize maybe even when the discovery was indirect?
Sorry.
If the discovery that you're going to make are indirect, the Z prime you mentioned, the composite X. So is there anything to say about the chance to characterize what you are discovering? For resonances that you produce on shell below 10 TeV, whatever, fine. But what about things that you are only seeing directly?
Well, so for indirect probe, right? So if the physics is heavy enough, you can use this EFT approach to characterize the effect. Or well, there are basically two kind of parallel approach, either top down or bottom up, depends, right? So the bottom up will just be the EFT approach, and top down you can try to make some kind of motivated models where maybe yes.
So I think this is a basic point, but it's very basic. But I think it's very, very important for all of us to know is that if we see any deviation from the standard model, okay, you can immediately turn that into a scale where perturbative unitarity breaks down. And then you have a concrete target for where new physics has to appear below that. We strongly believe that, right? Neutrinos, unfortunately, are giving us too high of a scale, so we're not guaranteed that it's going to be a scale that we can hope to probe in the future of mankind. But I think for these kinds of precision things, it may be very futuristic, it depends on the answer, but these scales are maybe lower than you think. If you take the ZZH coupling and you assume that the true value is 1 experimental sigma away, the current from the current bound, that theory breaks unitarity at 5 TeV, okay? So, I mean, I'm just saying, at least in the near term, what we're calling precision experiments are actually, if we find a deviation, there will be a scale that we can actually hope to explore in colliders. And I think that's something that we should definitely keep in mind. It certainly served us well in the past, this argument, right?
Some extent model dependent, but I guess the scaling is totally.
The way Chris and friends did it, you put the thing, the color that you find, you put it into your diagram, and you find that the theory violates the character.
That process, yes. Yeah,
This actually turns out in other processes, but the theory violates unitarity. Something has to.
I wanted to say when you or gather information on couplings over masses. Yep.
That's part of the paper that I actually wrote, and not just blah, blah, blah. Okay, so I guess I have to say that. But no, it is a coupling in a Lagrangian, and you can directly turn that into a you don't have to know G and M separately.
You will find 4 pi V for the standard model.
I think you agree. You're saying there is a bound, obviously, and you're saying we don't know. We still don't know what the mass is.
Yeah, you can verify that. It could be very far, but also, like I said, if tomorrow we found a deviation in ZBV, we'd be talking about 5 TeV.
Yeah.
With unitarity violence. So that would be the upper bound, not the place where some theorist thinks there might be something.
I mean, I agree with what you're saying, but I think it's important to ask whether you can characterize the model in case you are out of the reach of any realistic future collider. Because if the scales are 100 TeV, could be that you have enough sigma deviation that turns up at a 10 TeV muon collider, which comes from a particle at 100 TeV. And then it might be tricky, right? And nevertheless, I think that gave us a nice example that when you have enough observables that you can measure, and when you are willing to believe there is something that you're seeing, you can start to characterize the model with quite some accuracy. And indeed, we had in the BDKs at some point, 2, not 1, but 2. I think that. So in the case of the muon collider, you can imagine of starting to measure 2-to-2 scattering in jets, in muons, in electrons, and so on. And
About papers written, wanted to remind that somebody gave a presentation from early offshore production of this time, which was quite powerful in the end. Good. Just even if we just find enough. high energy. We will do regular observables, asymmetries, and if some reactions depend on how we build our detector, we really will pin down many of the Z prime properties, and you can also do flavor-specific couplings, quark couplings. We will know a lot more. I don't think it's just one anomaly solved. That's it. Just as the example mentioned about flavor, even for Z prime, as simple as Z prime, we will have a lot of diagnosis powers. Such a practice has been done to some extent for other high energy colliders. People did a lot of asymmetry studies, but I think Muon collider has it can also be done and hasn't been done.
Yeah, I totally agree. I think that would be something very interesting to look at.
The question is, later on you claimed, or maybe for other people's talk, the WBF is typically less powerful than direct production. That seems to be an oversimplifying statement.
Yeah, I mean, of course, here I'm just trying to give a very kind of rough estimation in terms of this E square over lambda square argument.
Well, but I'm interfering with standard model process, right?
Yes, of
Standard
course.
model process has 1 or S as well for drawing like processes.
Yeah, of course.
Yeah, so I'm interfering with a piece that is surprised. While we have lower S hat, may not be surprised. So this comparison seems to be just assuming there's only E or lambda scaling and any of the.
Yes. All the assumption here is that the BSM effect shows up as E square over lambda square. Oh yeah, absolutely.
Okay. Yeah.
Well, I mean, by saying E square over lambda square, I'm already assuming that it's an interference term.
Anything urgent before we move to the closing discussion over there? Thank you. Thank you.
So in all of your reactions, you show at most 2 bosons in the final state, but there's going to be the production of multiple bosons, and I didn't see any discussion of 2 Z's, 3 H's, W plus, W minus. I mean, the phase space is at 10 TeV. The space is there to produce many bosons simultaneously in the final state.
Yes, absolutely. So if I understand correctly, your question is about going beyond 3 or more final state particles, right?
Final state bosons.
Yes, absolutely. Yeah. So those are all the channels that you can explore. And typically, again, if there's any kind of a BSM effect, then they will kind of manifest also in those channels as energy growing behavior. So yes.
Right, but in the Higgs coupling measurement, why limit yourself to new Higgs-Higgs? You could include many different final states that include various numbers of Higgs bosons and other bosons in the analysis of the triple coupling and maybe even the quartic.
I think we're not yet at the point that these are really more constraining than those with fewer particles. You may get there if you do maybe 30 TeV collider or something like that.
No, I think it's I think it's there at 10 TeV, but
well, we are working out a fit with multiple final states, including those, and there are only selected cases where you can exploit those multiple bosons final states. So in general, it's still a losing game because of luminosity, at least 10 TeV, 10 attobal.
It does not. No, it does. I don't think it. No, it does not get small. I don't think it does. Are you sure it gets small?
It's a tail. It's a tail of PDFs. It gets smaller and smaller. And you need to probe the high IQ square if you want to be sensitive to these contact interactions. If you collect a lot of information at very low energy, only very slowly, you get some more information. So you can play a game. So if you do a PT bind analysis, the range of PT is between, let's say, around MZ. In some cases are actually as powerful as the tail, but eventually, if you try to go to very large PTs, you are really getting a low, too large statistical uncertainty. That's what that's why I said luminosity is the limiting factor at the moment. But we have few examples where this is almost not true, but very few examples.
I mean, there is a difference, however, between saying that you want to measure a standard model coupling and see this effect in the standard model versus BSM, right? Because of this energy growing behavior. And in fact, even at the LHC, right, there was this paper by Francesco Riva, Brian Henning, and I'm just forgetting because I'm old who else was on the paper, but even at the LHC, these things are on, plausibly on the edge, okay, when you take into account the fact that the EFT has some very strongly high energy growing behavior. Okay, so I don't know if this has been studied, but I absolutely think it should be studied, because even if you can't see the standard model, you could see a deviation from the standard model. Because the tri-boson production thing is I think pretty clearly out of, as far as I know, out of reach at the LHC. But some of these BSM effects, dimension 6 SMEFT effects, are not.
I don't know how many people is trying this. I can tell you it is in our radar, and in some cases that's I mean, the inspiration comes from the exact same paper, Higgs without the Higgs, from Francesco. Yeah, that's the title. And to my dismay, because I first I had to convince Xing to compute it. It didn't work. No, it's correct, but it's a matter of how much luminosity you can spend on that. And it is not, yeah, but it's enough to be a factor 3 off, and you're irrelevant when you combine. Anyway, that's a beautiful idea, and I think it's appreciated in the field that you can also try that. I think I try to say that even for FCCHH, not just for Muon Collider, because there you may have better luck. We have not tried yet, but I think in Francesco's time this was already too early to think about very far future. But it should be studied again with FCCHH in mind as well. But let's thank Xing before, because I think we are moving to discussions.